Okay. Our second talk of today is from Andreas Schachner, who is going to tell us about the standard model quiver from singular de Sitter string compactifications. Take it away, Andreas.
Yeah, thank you, and welcome everyone. I want to start by, of course, first of all, thanking Cody and John for organizing this beautiful seminar series, which allows all of us to present our work during these troubling times. So today I would like to talk about a project in collaboration with Michele Ciccoli, Iñaki Garcia Echevarria, Fernando Quevedo, Pramod Shukla, and Roberto Valandro on realizing the standard model quiver from singular de Sitter string compactifications. Specifically, we consider global type Dp compactifications to 4 dimensions on Calabi-Yau threefolds, where the standard model is realized on a single D3 brane at a Dp5 singularity. These type of constructions from branes at singularities have many appealing features. For example, since the visible sector is localized at a single point in the compactification space, it is easy to decouple the standard model degrees of freedom from the hidden sector degrees of freedom. Furthermore, this implies that one can address global and local issues separately, where global issues, for example, include tadpole cancellation or modular stabilization, while local issues include, for example, the standard model gauge group and the chiral spectrum. Finally, I would also like to stress that there's a largely unexplored class of phenomenologically interesting models from D3 branes at the Pezzo singularities, which we would like to investigate further in the future. Now, given that I'm talking so much about the Pezzo surfaces, let me give you a proper definition. So the Pezzo surfaces are complex 2-dimensional Fano surfaces, which means that they are projective algebraic surfaces with ample anti-canonical divisor class. And we distinguish P1 times P1 and Dpn corresponding to P2 blown up at endpoints. And the following, we will mostly ignore the exception P1 times P1. Now, by putting branes at these types of singularities, this leads to models with very attractive features. For example, one can generate a huge variety of different gauge theories from a single deep brane probing these types of singularities. Furthermore, the quiver gauge theory associated with these types of constructions always comes with 2 anomalous E1s, which is of course critical for model building aspects. Furthermore, we would like to have a chiral spectrum which arises from intersection of 2 and 4 cycles in the singular geometry. And one can show that the Pezzo devices inside the Calabi-Yau threefold are the unique type of 4 cycles that can be shrunk to a point using Grote's criterion, which was, for example, explained in these 2 papers beautifully. I want also mention that this work is part of a series of papers by some of my collaborators, where they previously constructed many global constructions. And we extend this type of construction today by looking at the Dp5. Now, how do we describe the world volume theory from a D3 brane at a Dpn singularity? Here we take on a large volume perspective by looking at a complex cone over one of these Dpn singularities and deform the killer structure in such a way that we blow up certain cycles inside a singular geometry by giving cycles finite volumes. And in this large volume limit, the D3 brane splits up into so-called fractional branes, which themselves are bound states of D branes supported on cycles in this geometry. They can be described through sheaves, but for today's purposes, you can think of sheaves simply as being vector bundles supported on certain submanifolds. And for the Pezzo surfaces, one needs n+3 fractional branes to describe this single D3 brane probe. Each of these fractional branes is characterized by its Chern character or Ramon charge vector, which comes with a D7 wrapping number around the Dpn, a D5 component from wrappings around 2 cycles, as well as an instantal number. Now, the massless spectrum associated with open strings stretched between different fractional branes is nicely encoded in these extension groups, which are generalizations of the cohomology groups to sheaves. For today's purposes, it's sufficient to compute the number of states appearing between different fractional branes, which can be computed using this relative Euler character, which is a weighted sum of the dimension of these groups. And for further details, you can have a look, for example, in this nice reference by Belinda and Weinhold. For so-called exceptional collection, which is a very special basis of fractional branes, the spectrum becomes completely chiral and is completely encoded into anti-symmetrized intersection matrix, so the anti-symmetrized version of this relative Euler character, which only depends on the rank, so the D7 component, and the degree of the fractional branes. And further details on exceptional collections can be found, for example, in these two references. Now, using this expression for computing the spectrum, we can now continue and look at the quiver for the Dp5. Here we follow the seminal work by Weinhold on the geometry of particle physics and define an exceptional collection by this data shown here. And then it's easy to plug this expression into the formula for the spectrum and obtain this, this nice matrix, which has a certain block-like structure. To interpret this matrix, we draw nice diagrams, so-called Quiver diagrams, by assigning to each fractional brane a node I, and if there are n I copies of such a fractional brane, it is associated with an additional u of n gauge factor. If there are chiral multiplets in the bifundamental of two gauge group factors, then we draw a line from node I to node j. Now, using these rules and noting that in this matrix, each non-vanishing entry corresponds to drawing an arrow from one node to another, we can translate this matrix into the Dp5 Curve Diagram, which is shown here. And as you see, for example, in each line, there are only 4 non-vanishing entries. And notice that the sign corresponds to the direction of the arrow. You see that at each individual node, only 4 lines are being attached. Now, further, notice that anomaly constellation gives some constraints on the ranks of the individual gauge group factors. Now, next up, I would like to stress that if you were to draw a quiver diagram for the standard model itself, you would realize that this quiver itself, without any further extension, must be unoriented. And therefore, this motivates that we also look at the orientifolded version of our Dp5 quiver. How do we orientifold over quiver gauge theory? We use the following 3 rules, which are, for example, explained in this reference here. So an O-plane involution defines a Z2 automorphism of the quiver that leaves the original superpotential invariant and also identifies chiral and vector superfields on either side of the involution. In this talk today, I only mention one of these projections. In our paper, we discuss 2 separate projections. The projection I would like to discuss here is the following. So we take a projection that takes node 1, 2, 5, and 6 onto themselves and exchanges nodes 3 and 8 and 4 and 7. Focusing on a USPN projection, this leads to a nuclear diagram shown here on the right, which has 4 USPN factors and 2 UN factors. The different bifundamental metafields are related under this projection using these formulas. Now, of course, our quiver so far doesn't look anything like the standard model. In particular, there are many missing features, like we don't have 3 chiral families, and we have a far too big gauge group, as well as we are missing some non-chiral matter. It turns out that all of these issues can be resolved by turning on VEVs for bifundamental metafields. And this has a nice interpretation in terms of fractional branes by building bound states of fractional branes, condensing some of the nodes in the original quiver into new nodes in the Higgs quiver diagram. And geometrically speaking, this corresponds to partial resolution of the singularity. So how does this building of bound state work? So we take a bunch of fractional branes at each of our nodes, and then we take a linear combination of all of the charge vectors, where the multiplicities appearing in the sum are illustrated in this diagram up here. We can condense all of these fractional branes to a single node by turning on VEFs for our bifundamental matter fields. And turning on these VEFs, we find that in the Higgs quiver, we have only a single node corresponding to our bound state. Okay, so fair enough, but this is a far too boring situation. So let's build another bound state, now illustrated here in red. By putting these additional fractional branes at each of the nodes, we increase the rank of the associated gauge groups. Now we want to Higgs this quiver down to a new quiver with only 2 bound states. This can be achieved by turning on VEFs of this form. Now you might ask, okay, this seemed so far kind of arbitrary. So what's the point of building these bound states? The point is that now if we include further fractional branes at nodes 3, 4, 7, and 8, which do not contribute to any of these bound states, this means that we just assign some additional zeros in our VEFs here. The Higgs quiver diagram has this nice structure, which shows that indeed we find a spectrum of 3 chiral families. And the breaking pattern shown here on the bottom left has been verified computing the mass matrix for the gauge bosons. And we confirmed indeed that using these VEFs that this breaking pattern is realized. Now, after orientifolding, our quiver has the structure here where the USP2 can be simply thought of as an SU2. And so once we assign definite values for n and m, for example, if we assign n equal to 3 and m equals to 1, this is nothing but a left-right symmetric model. Whereas for n is equal to 2 and m is equal to 4, this is the particellar model. And in the following, let's focus on the first choice. So fixing n and m, we indeed find almost the spectrum of the SUSY left-right symmetric model, represented by this quiver diagram shown here. And there are a few comments that I want to make. So first of all, there are 2 U1 factors appearing in this quiver diagram, of which one combination is non-anomalous, corresponding to U1b minus L. There's another combination that is anomalous, which gains a Stickleback mass through the Green-Schwarz mechanism, but it remains as a global anomalous symmetry in the low energy effective action. Now, concerning the non-chiral matter between the 2 SU2 states, it was shown by Weinhold already in his paper that there are mass terms that are generated from superpotential couplings that ensure that only 2 vector-like massless pairs remain. Some of you might have already noticed that we are missing a few non-chiral states. And indeed, in order to Higgs this model down to the standard model, we also need some non-chiral states between the SU2R and the U1 factor. And these 2 vector-like pairs can be realized by building more complicated bound states, starting from a larger quiver. And this is explained in our paper. But given the time limitations today, I'm not going to show this in detail. And you should take for granted that you can really generate these additional non-chiral states. Now, finally, to get to the standard model, you use conventional Higgsing to break the SU2R times U1b minus L down to the hypercharge U1, which is, for example, explained in this paper by Heckmann, Waffer, Welinder, and Weinhold. Okay, what you end up with is precisely the minimal quiver standard model. So this is great news. We just managed to realize the standard model on a single D3 brane at a Dp5 singularity. Now let's come to the more pressing issue of constructing a global embedding. So for our global embedding, we have a few desirable requirements. So first of all, we would like to have some Dp5 divisor that allows us to have a Dp5 singularity in our compact Calabi-Yau threefold. Furthermore, we need a few rigid divisors in order to support instanton effects that are necessary to stabilize Kähler moduli. And also the involution needs to leave our Dp5 divisor transversely invariant. Now, taking all of these requirements into account, we began looking out for suitable Calabi-Yau threefolds. So first, we have to formulate some sufficient conditions to finding the Pezzo divisors in the Calabi-Yau threefold. So first, a divisor that is of the Pezzo type, for example, has to satisfy that the triple self-intersection number must correspond to the degree of the Pezzo surface. Now, additionally, we have to have a so-called diagonality condition for our Dp5 divisor, which again can be expressed in terms of triple intersection numbers, which ensures that you can write the four-cycle volume as a complete square, which means that you can squeeze the Calabi-Yau threefold along a single direction and thereby generate the singularity. We refer to these types of diagonal DPN divisors as DDPN divisors. So the first thing we did was we looked for certain divisors inside Calabi-Yau geometries in the Kreuzer-Skarke database with H from 1 up to and including 5. And we looked at all of the favorable geometries and listed all of the Del Pezzo divisors that you can find in these geometries. Now, interestingly, once you impose the diagonality condition, all of the diagonal DDPN divisors disappear with n between 2 and 5. And this very peculiar observation led us to formulate the following conjecture that Calabi-Yau threefolds arising from fine regular star triangulations of 4D reflexive polytopes in the Kreuzer-Skarke database do not exhibit diagonal DPN divisors with n between 2 and 5. Of course, some of you might already intervene and say, okay, we only checked a really, really tiny part of this Kreuzer-Skarke database. And I certainly agree. So we further checked 200,000 geometries for larger Hodge numbers using the Calabi-Yau tool package of the Cornell group, which confirmed this trend. So it seems like there's something more to this observation, and it would be interesting to understand whether this holds true in more generally, and whether there's some fundamental reason for why these types of divisor structures cannot appear in the Kreuzer-Skarke database. Now, it seems a bit dramatic for our purposes because now we have to look out for other classes of Calabi-Yau threefolds. So the crucial insight that we need to construct different types of Calabi-Yau threefolds is the following. The Dp5 surfaces can be constructed as biquadratics in P4, which means that they can be realized at the intersection of two quadratic polynomials in P4, given by this GLSM data. So the plan for constructing Calabi threefolds becomes that we construct these threefolds as the complete intersection of two equations in a 5-dimensional toric space. And once you restrict to a 4-dimensional ambient space, you should get back the biquadratic equation for the Dp5. And using this idea, we constructed 6 different Calabi-Yau threefolds in our paper. But here, let's focus on one specific example. So this specific example has H from 1 equal to 3 and is represented by this data here, where we have 2 Dp5 divisors, which is already good news. And it turns out that the divisor at the coordinate x3 is diagonal and can be taken as our singular divisor that hosts the D3 brane realizing the local model. Now, in a basis of smooth divisors, we can define the Kähler form and then compute the volume form for this specific Calabi-Yau threefold, which is indeed of Swiss cheese type, which is necessary later on when we stabilize Kähler moduli using the large volume scenario. An orientifold involution for this model is given by taking x5 to minus x5, which puts a single O7 plane on the divisor D5. We checked explicitly that we can embed our local model into this Calabi-Yau threefold. And we also checked that the global and local involutions that we defined here and previously are consistent. And for more details, I refer to our paper. Now we take the singular limit by taking the two-cycle volume of T3 going to 0, which gives us a Dp5 singularity at a coordinate x3 is equal to 0. Now next up, we have to discuss a D-brane setup, because first of all, we need some D7 branes in order to cancel the D7 tadpole induced by the O7 plane. And furthermore, we need an additional D3 brane hosted on the second Dp5 divisor, which then supports non-perturbative effects. Concerning the former, we put a stack of 4 D7 branes plus 4 of the images on top of the O7, which leads to a hidden SO8 gauge group sector. And then we also need to turn on some flux on the D7, which will be necessary further down the line. Secondly, we put a D3 brane on top of the Dp5 divisor at x4 is equal to 0. And in order to ensure that this D3 brane gives rise to an O1 instanton, we have to ensure that, first of all, the flux vanishes, as well as that the free-to-Witten quantization condition is satisfied. And indeed, this can be achieved by turning on half integral flux of this form. Finally, one has to check that this instanton indeed contributes to the superpotential by checking the absence of chiral zero modes at the intersection of the D7 with the D3. And this leads to setting the flux N4 is equal to 0 in this formula above here. Now the flux on the D7 breaks the SO8 gauge group down to U4, which means that there will be also an induced Fi term. And this Fi term is in fact non-vanishing for integral flux choices NB. And this non-vanishing Fi term implies that we also have to switch on a VEF for the adjoint scalar living on the D7 stack, which leads to a T-brane background. And this can be seen directly, for example, from the 8-dimensional equations of motion, which imply for non-vanishing flux that you need to have some non-vanishing VEF. And this in 4-dimensional leads to vanishing D term. Under this breaking, the joint scalar decomposes in this particular way, where the red blocks correspond to open strings on either the stack or on the image, while the off-diagonal blocks corresponds to open strings stretched between the stack of D7s and the image with the two orientations. Now, in our case, we choose to turn on a VEF on the upper triangular block, which means that some of the D7s recombine with some of the image D7s. And consistency conditions for turning on this VEF imply that we have to pick a flux NB on the volume divisor to be equal to 1. All in all, we can compute the total D3 charge coming from D-branes and O-planes. And this is given by this formula here, which contributes then to the tadpole cancellation condition and limits the amount of flux that we can put on the Calabi-Yau threefold. Finally, we have to talk about the issue of modular stabilization. So first, we define our usual Kähler potential with the alpha prime cube corrected part appearing in the Kähler sector here, together with a contribution KQ coming from the visible sector. And the superpotential, we have as usual a flux contribution, an instanton contribution, as well as a Quiver contribution from the visible sector. Now, putting all of that into the formulas for the D and F term scalar potentials, one finds several different contributions. And at leading order in the volume, namely at volume to the -2, we can stabilize some of the moduli supersymmetrically. So first, let's have a look at the Quiver D terms. For the Quiver D terms, we can look at the non-abelian Quiver D terms. This leads to 4 constraints on 40 real parameters in the webs. So this is easily realized. And using these 4 constraints, one finds that the abelian Quiver D terms automatically vanish. So there are no Fi terms generated for the anomalous one. Finally, for the Quiver F terms, we use the large amount of tuning possible from the 36 unfixed real parameters from the webs, plus the fluxes in order to satisfy these conditions. Of course, on the bulk side, we have a flux scalar potential that stabilizes the axial dilaton and the complex structure moduli by solving the F term conditions. While for the D7 brane, we have a D term contribution for the open string moduli, which is of this form, and which can be set to 0 by stabilizing the open string modulus in this particular way. Now we're almost done. The only thing left to do is to also stabilize killer moduli. So for that, we look at the LVS scalar potential at leading order in the volume, which can be written in this particular way. And then taking into account that there is a contribution from soft scalar masses, which is of this form, we can put everything together such that the total scalar potential can be written in this form, where this contribution comes from the soft scalar masses. Now, minimizing this potential, one finds that the vacuum energy at the non-SUSY LVS minimum is given by this formula here. Now, by setting this bracket to 0 or making it slightly positive, you can either find Minkowski or de Sitter minima. Now let's give, I want to show you a few explicit values for Minkowski minima. So here there are a few numerical solutions for different choices of GS, where you see that the smaller we take GS, the larger the volume becomes. However, at the same time, we have to decrease the ratio W0 over A3. Now, to achieve such small ratios, we probably have to tune W0 very small. And this tuning can be achieved by either using the analytic solutions provided by the Cornell group, for example, or using stochastic search optimization methods such as genetic algorithms, which have been applied by Alex, Gary, and myself 2 years ago. Also, these values should be taken with a grain of salt because these are certainly very model dependent, and we expect that the situation can be improved by either using models with more moduli, using Gaugino condensation instead of instantons, or using other uplifting sources, which however also means that we use some of the explicitness, which makes T-branes so attractive. So let me conclude. So I hope I convinced you that that models of T-branes at Del Pezzo singularities are very appealing to realize the standard model. In particular, I showed you today how the standard model Quiver can be realized on a single D3 brane at the Dp5 singularity. I further provided an explicit construction of a compact Calabi-Yau threefold together with a consistent global embedding, and show that we can stabilize the moduli in a de Sitter minimum from a T-brane uplift. And there are several directions that we would like to explore further in the future. For example, we would like to combine this model with a model of inflation. And also, for example, to my knowledge, there is no good understanding of these types of models in the F-theory language on singular basis. And it would be really interesting to investigate these types of models in the F-theory language as well. So I think I'll stop here, and yeah, thank you everyone for your attention.
Okay, thank you, Andreas, for the very nice talk. Let us all thank Andreas with our clap emoji. Let me ask the first question. So you had this diagonality condition on the del Pezzo.
Yep.
Can you remind me why that was necessary?
That takes too long. Let me jump to here. So you mean this condition over here, right?
Yeah, exactly. Yeah. Why did you need that condition?
This condition was necessary because now you only have to take this linear combination of two cycle volumes going to zero, and you don't have to squeeze the Calabi-Yau along two different directions, which would make the singularity much more complicated than a simple del Pezzo singularity, because you will probably have some intersection with another divisor.
I see, but it could still work. You might just tune another singularity and get some additional light matter somewhere else, or light fields, but the rest of the construction, I don't see anything.
That could certainly be true, and that's certainly something that we might consider in the future, given that it's really usually one takes that condition because it just makes your life easier, right? And now we realize that, okay, imposing this condition actually is a quite strong condition, which led to all of these zeros here in this table. So I certainly agree that one could consider ignoring this additional condition. I agree.
Yeah. Do you have at any point any understanding of why of those zeros in the table geometrically?
I really don't have a good understanding from that. It's a bit mysterious. I mean, for example, personally, I would say that there's a difference, for example, going from the Dp4 to the Dp5, in the sense that the Dp5 comes itself with complex structure deformations. So it could have been that for some reason that you can't embed the Dp2 to Dp4, but you can embed the diagonal Dp5. However, the gap seems to start between 5 and 6, which seems to, at least to me, a bit mysterious. And so far, I think we don't have a good argument for that. So yeah, it's an interesting observation. Yeah,
that is interesting. Okay, well, are there any further questions? If not, let us thank Andreas again for the excellent talk.